Fusion Mobile, quality e-learning experience on the go.
Welcome to Fusion Mobile e-learning clinic. My name is Sonia Lalo and I've been walking you through the physics class. Today I want to consider the models of atoms and nuclear physics. Models of atoms and nuclear physics. To begin with, we'll be considering the models of atoms. Then we'll talk about the atomic structures and properties. We'll look at nuclides and isotopes. Then we'll talk about radioactivity, nuclear reactions, and nuclear energy. Alright, let's give it a start. Models of atoms. Over the years, different scientists have proposed different appearances of what the atomic structure is like. At the beginning, J.J. Thomson he discovered the electrons, and it was like an atom is made up of different components and all of them are just scattered. That is, he drew his own structure, claiming that the atom contains positives and negatives all over the place, something like that, with no uniform anything. But of course, this was discovered not to be true when another scientist, Rutherford, discovered that an atom actually has a nucleus. He discovered that the atom has a nucleus. This led to further experimentation, and then Bohr came up with the idea that Rutherford came up with the idea that the atom had a nucleus. The nucleus carried most of the weight of the atom. Then Bohr conducted an experiment, and that led to the discovery of what is called the electron cloud. That is, in that particular model, it is believed that at the center of the atomic structure, we have our positive charges stored. We have our positive charges all packaged, and then we have our electrons scattered all over the place. Now, this particular theory tends to believe that the electron clouds are not really particles. It senses them more like waves, because it does not really arrange them. It just tells they are all scattered all over the place. They move at their own will. It was all because of the limitations in the resources and information available to them that led to all these beliefs. But today we've come to a better understanding of what the electron's structure looks like. We'll come to a better understanding of what the atomic structure exactly is like. But before we go further into talking about what the atomic structure is like, I haven't spoken about this. We'll take a short break, and in the short break, a question will be displayed on your screen. You're expected to answer. We want to see how much you understand what has been taught in this lesson so far. Welcome back. So, we've talked about the Bohr's experiment, and also we've talked about Rutherford's experiments and J.J. Thomson's discovery. So, what exactly does the atomic structure look like? Every atom is made up of elements. Every element is made up of, or every atom of an element is made up of certain particles. These particles are three. We have the proton, which is also known as the positive charge. We have the electron, which is known as the negative charge, and we have also the neutrons. These have no charge, but have a weight. They have a mass. Now, at the core of the atom, that is in the center of the atom, at the nucleus of the atom, the weights of the proton and the electron are packaged there. They have different types of elements. Different elements have different number of atoms in their different number of protons and neutrons in their core. We have some who have more protons than neutrons. We have some who have more neutrons than protons, and we have most of them which actually have equal protons and neutrons. But for us to have a clearer understanding, that was one of those things that led to the creation of those things we call atomic number, mass number. So what is the atomic number? The atomic number is a representation of the number of protons contained in a particular element or in a particular atom. The number of protons contained in a particular atom. The proton number is represented by Z. Also, we have what we describe as the mass number, which actually can be described as a nucleon number. The nucleon number. The nucleon number is a sum of the entire particles contained in the nucleus. It is represented by A. This accounts for what is described as the mass number of the atom. So this actually are the major things that we use to identify the atoms. So if you want to know the number of neutrons in a particular atom, all you need to do is you take a difference between the A and the Z. So A minus Z will tell us the total number of neutrons in the atom. I would give some examples. In fact, some examples will be displayed on our screen just about now. From the screen, you will see the table that is showing hydrogen, carbon, sodium, copper, and uranium. Of course, you see that in hydrogen we have one nucleon number, one proton number, which suggests that there is no neutron. We also have carbon that has 12 nucleon number and 6 proton number, which suggests that there is 6 neutrons. And also you see elements like uranium that have 238 nucleon number and 92 proton number, to suggest that it has much more neutrons than protons. About 146 is the difference. 146. Talk about the nuclides and isotopes. Nuclides and isotopes. An isotope, when we say a particular element is an isotope of another element, it suggests that the element contains one of the elements, both of them have the same number of protons. That is, the number of protons is the same, but the number of neutrons contained in them differ from one to the other. They have the same number of protons, but different number of neutrons. Well, there are very many of elements do have this, exist in these isotopic forms. In the isotopic forms, a very good example is chlorine. Chlorine is represented as 1735, and it also exists as 3717. Now, these are two different isotopes of chlorine. One of them has a nuclide number of 35. The other one has a nuclide number of 17. The one that has nuclide number of 35 will take a difference. That's 35 minus 17. It gives us 18. So it has 18 neutrons. While the other one, 37 minus 17, gives us 20 neutrons. So it is possible for an element to actually have different number of neutrons in it and remain the same element. Yes, it is very, very possible. It is still the same kind of element, it's still the same kind of atom, so long as the number of protons remain the same. We have very many of these kind of elements that exist and show isotopy, and these are most of their isotopes are what are used in radioactivity. The more the variation of the system, the higher the likelihood of it being a radioactive substance. Where's my voice? Radioactive isotopes find their functions in many aspects of our day-to-day lives. We see them come up in the carbon dating, or of course carbon dating, just as it says, it is kind of taking a particular isotope of carbon and using it to find the age of a particular element or a thing. Of course, we also see them, that's in archaeology. We use them also for dating of other things. We use them in sterilization of equipment. We use them even in the lab, in the in medical world. Use them for making some medications and other things as that. Because of the difference in the system, because of the way the system, because of this difference in their appearance, that is a nuclide structure, some of these materials are actually unstable when they get bombarded by a neutron or sometimes even waves. They lose certain properties and alongside lose energy as well. So some of them, many of them are called, many of these isotopes are radioactive. So we call them radioisotopes. Radioisotopes. So a radioisotope or a radioactive isotope is an isotope that when it is being bombarded with a neutron charge, as in with a neutron atom, with an atom of a neutron, it generates energy. It gives off energy. That brings us to radioactivity. Inside radioactivities, there are certain things to put into consideration. Those include part of those things we should consider include the half-life of a thing. On your screen, some definitions will be there. Now, the half-life, radioactivity is defined as the spontaneous decay or disintegration of an unstable nuclear, and it can happen with the release of a gamma, beta, or an alpha radiation. Also, the half-life of a substance or a radioactive decay is described as the time it takes the sample to reduce by half of its original value, or the time it takes the radioactive nucleus to reduce to half. Of course, all this, well, on your screen also you'll be seeing different kinds of radiations that are emitted. We have the nature of alpha particle. Alpha particle appear like helium. They have velocities that are really quite low. They possess a charge which is a positive charge. They are slightly deflected by magnets, and of course they have heavy ionizing power. Beta particles have a medium penetrating power. Alpha particles can be stopped by paper. Beta particles require several millimeters of aluminium to stop them. They have a lower mass compared to alpha particle. They have a higher speed than alpha particle, and of course they are high speed electrons. They are negatively charged. They are electrons. While gamma particles are radioactive, they have very short wavelengths. They are traveling at the speed of light. No charge. Mass is next to nothing, no effects, no response to magnetic effects, little ionization energy, but high penetration energy, or high possibility of them penetrating up to about several centimeters of lead. When it comes to half-life, the half-life of a particular system is given by the expression, the change in volume or mass, original volume or mass multiplied by time. With this expression, we can calculate, this is radioactive decay. So how long would it take half of the entire radioactive substance, that's the half-life? It can simply be calculated as T half-life equals to lambda divided by no, let me check. So our time for half-life to decay can be calculated by 0.693 divided by lambda. Of course, our lambda is our radioactive decay constant. Alright, let's talk about nuclear reactions. nuclear reactions. There are two major types of nuclear reactions. These are nuclear fission and nuclear fusion. Nuclear fission and nuclear fusion. While nuclear fission has to do with you breaking down a complex we have fission and fusion. While fission has to do with you breaking down something, splitting a cell, an atom into many parts, fusion has to do with you adding something to a system. So we have radioactive decay is a fission process where you just leave like your uranium, you leave it probably in presence of it breaks down into something simpler. That is a fission process. But in the when you bombard to create more energy, of course you use a lot of energy to bombard, but even a greater energy would be created in the fusion state. So we can define nuclear fission as radioactive decay process. There's a decay process in which an unstable nucleus split into two comparative parts. It's a situation where an unstable nucleus splits into two parts, while nuclear fusion is the joining of two or more lighter nuclei to form a greater one, a bigger one. Let me draw on the board at least one or two a chemical, what they look like. So we can have an expression for nuclear fission. In this particular one, you see a particular atom is being added, and of course it breaks down to give many other components. It's just like you are cracking your petroleum produce to get petrol, kerosene, and other things that can come out of it. This one is you adding up. So when you add up in the next level, that's H21 plus 11H. It will give an isotope of helium and to give us a gamma radiation and also a large amount of heat. And also if you add up another time, it will give up, if you add to this helium again, you will have your proper helium now created, and you would also have a neutron that will be given off no charge plus a lot of energy. So all this, if you observe, there is always a release of energy. There will be release of energy in both fission and fusion. But of course, if you look at it, this one has just one energy and we're having 1, 2, 3 different levels of energy. So we have even much more higher energy being released from nuclear fusion compared to nuclear fission. Alright, let's quickly consider nuclear energy. Nuclear energy, what do we mean by nuclear energy? It's an energy that is created from nuclear reactions. It's an energy created by a nuclear reaction. Sir Albert Einstein gave us an expression that is today being described as the great expression. That is, some people describe it as the almighty expression, which simply says E equals to mc squared. That's the expression that has been used in the creation of many devices. It's an expression that has been used to find our ways to many top highs. It's one of the ways in which we have been going on our space expeditions. E equals to mc squared by Sir Albert Einstein. Sir Albert Einstein, in his research on relativity, he concluded that this expression would give, of course, it's a change in mass. Yes, change in mass. It will give the amount of energy that is required for binding an atom structure together. So, either for splitting or binding the molecules of the neutron and the proton to the nucleus of the atom. So, this particular expression finds its use, and it is also being used to calculate the amount of energy that is being liberated in the fission and fusion process. When we consider those two experiments that we indicated on the board, the fusion process produced so much. The first one of each of the fusion process, that is the final energy from the fission process, produced even less than what each of the fusion processes produce as output energy. This suggests that the nuclear fusion has a higher energy producing chance than nuclear fission, that is FU. It produces more than fission. So, fusion has chance of giving us more energy than fission has the power to give. Also, it is worth to note that the applications of nuclear energy reactors, we use them for making atomic bombs, explosives. We use them for making nuclear reactors. Apart from nuclear reactors and all these other things, we can use them also for creating generation. We can use them in the generation of electricity, in medical, and even in the sterilization of our food containers. So, nuclear radioactivity has a lot of benefits to mankind. Of course, the production of gamma ray X-ray, they find their use in the medical line for taking pictures of internal organs, observation of the interior of parts of humans. So this also fall under some of the usefulness of radioactivity. In this lesson, we considered models of atom and nuclear physics. We talked about the model of atom. We discussed 3 different models of atom: the one by J.J. Thomson, the one by Neil Bohr, and the one by Rutherford, and the one by Neil Bohr. We looked also at the description of Neil Bohr as cloud of electrons. We then came into talking about the atomic structure, that is, the nucleus always accommodates the proton and the electrons, and the proton and the neutron, while the electrons move around in orbitals. We then looked at nuclides and isotopes. We said when the nucleus, when we have the same number of protons but different number of neutrons, we say those substances are called isotopes. They are related to each other. We then looked at radioactivity, that's the ability of a substance to break down because of maybe it was unstable, it's split into 2 or into other parts. And then we looked at nuclear reactions. What do we get? What types of nuclear reactions? We talked about fission and fusion, and we explained that fusion produces more energy than nuclear fission. Okay, I haven't spoken of all these topics. In a few seconds, some questions will be displayed on your screen to check your understanding of this particular lesson. If there is any difficulty you found in the course of the lesson, you can go over the video another time, to get a better clarity on what has been taught. Thank you.